students, new topic, finite automata with output generator. See, finite automata classified into two categories. First one is finite automata without output, known as acceptor. This again classified into three categories. First one is DFA, second is NFA, third one is epsilon NFA. Already we have seen these three. The expressive power of these three are equal. Clear? Now, second category of the finite automata is finite automata with output. These are the output generator. Again classified into two categories, Moore machine and Mealy machine. Moore machine and Mealy machine. The expressive power of Moore machine and Mealy machine are same. What do you mean by this? We can convert every Moore machine into a Mealy machine and Mealy machine into a Moore machine. Clear? Please note this. Okay. Now, next setting is Moore machine and Mealy machine. Moore and Mealy machine. Moore and Mealy machines are output generator. Clear? Moore machine and Mealy machine are output generator. Clear? That's why there is no final state. There is no final state concept in Moore machine and Mealy machine. Moore machine and Mealy machine. Clear? Moore and Mealy machine. Because they are not recognized any language. Both are deterministic in nature. Moore and Mealy machines deterministic in nature. What do you mean by this? It means they behave like a DFA, deterministic in nature. It means each and every state have exactly one transition on every input symbol. Both are deterministic in nature. What do you mean by this? Each and every state have exactly one transition on every input symbol. Clear? Now, we start Moore machine. Moore machine. Moore machine. See, what are the points of Moore machine? What is the definition of Moore machine? Definition. If output symbol is associated with, if output symbol is associated with each state of finite state machine, then such automata called as Moore machine. Clear? For example, Q naught output associated is this, Q1 output associated with this. Suppose like that. Clear? A associated with Q, output B associated with Q1. Clear? Clear? Next point. It cover the transitions for all strings over the given alphabet. What do you mean by this? Each and every state have exactly one transition on every input symbol. Clear? Next point. If the input is n length, then the output of the Moore machine, if the input is n length, suppose input is 3, length is 3, then output of the Moore machine is length 4. Why? Because initial state generate the output without reading anything. Clear? Note down these 2 points. If input string length is n, then the length of the output string generated by Moore machine is n plus 1. Clear? Next, Moore machine generate the output associated with initial state by reading no input symbol. That's why the length of the output is +1. Clear? This is the description of the Moore machine. After that, we will see mathematical description of this. Clear? See. Clear? Now, mathematical specification of Moore machine. Of Moore machine. It contains 6 tuples. Moore machine. It contains 6 tuples. Please see. What are the 6 tuples? Capital Q. What is capital Q? Set of finite states. Sigma input alphabet. Q naught initial state. Delta transition function. This delta output alphabet, and lambda is output function. Lambda is output function. See, first, capital Q, finite set of states. Sigma input alphabet. Q naught. What is Q naught? Initial state. Q naught initial state. Next one is delta transition function. Deterministic in nature function. What is transition function? Delta Q cross sigma implies Q. Clear? Next is this delta output alphabet. That are finite. Output alphabet are finite. Next is lambda. Output function. Lambda depends on the only state. Lambda depends only on the current state. Clear? What is lambda? Q determines delta. This question can be asked in GATE. in Moore machine, output function depends on only on current state, only on current state. Clear? Clear? Please note all these points. Yes, done. See the example. Construct construct a Moore machine, that takes set of all strings a comma b as input and print one as output for every occurrence of AB as a substring. What do you mean by this? If AB is come, then it prints 1. Otherwise, it prints 0. Otherwise, print 0. Otherwise, print 0. Clear? Please see. Listen carefully. What is sigma? Sigma is A and B. What is delta? Output alphabet is 0 and 1. If AB is come, then it prints 1. Otherwise 0. See. Q0 A Q1 B Q2. If AB come, it prints 1. Otherwise, it prints 0. Suppose the input length is 2. AB is input. Then what is the output? Output is length 3. Initially, we visit Q0, it prints 0. When we visit reading A on Q1, it prints 0. When we read B goes to Q2, it prints 1. See, output is length 3. Why? Because without any reading, initial state print the output. Now, make this diagram as deterministic. B A B. Check. C AB it prints 2 times 1. Initially on Q0 it prints 0. Read A on Q0 it goes to Q1, it prints 0. Read B on Q1 it goes to Q2, it prints 1. Read A on Q2 it goes to Q1, it prints 0. Again Q1 it reads B, go to Q2, it prints 1. AB is come 2 times and 1 print 2 times. Clear? See? Any doubt? Okay. Next example. Next example. Construct a Murray machine that takes set of all strings A's and B's and counts number of occurrence of substring BAA as one, otherwise print 0. Please try to do this question. Have you done? No. See, whenever VAA is come, it prints 1. It prints 1. See, Q0 is the initial state. Read B goes to Q1. Read A goes to next state Q2. Read A goes to next state Q3. Then it prints 1. Otherwise print 0. Otherwise print 0. Now make us DFA. B A B See, suppose this is the input A, B, A, B, A. What it will print? The length of the input string is 7. It prints output with 8 length. Initially on Q0 it prints 0. Read A, again it prints 0. Read B goes to Q1, it prints 0. Read A on Q2 it goes to, read A on Q1 it goes to Q2, again print 0. Read A on Q2 it goes to Q3, it print 1. On Q3 it reads B, go to Q1, print 0. On Q1 read A, it goes to Q2 and print 0. Read A on Q2 it goes to Q3 and print 1. See, this is the output. This is the output. What is the transition table for that? Please see the transition table of this. How to represent the transition table? Input alphabet AB. Output is associated with the states. What are the states? Q0, Q1, Q2, Q3. Output associated with the Q0 is 0, Q1 is 0, Q2 is 0, Q3 is 1. Clear? What are the transitions? Q0 on A, Q0, Q0 on B, Q1, Q1 on A, Q2, Q1 on B, Q1, Q2 on A, Q3, Q2 on B, Q1, Q3 on A, Q0, Q3 on B, Q1. Please check. Clear? Okay, next question. Construct a Murray machine construct a Murray machine that takes set of all strings of zeros and ones and produce A as output if input end with 1010 or produce output B if input ends with 1 1 otherwise produce C. Otherwise produce C. It means input alphabet is 0 and 1. Output alphabets are A, B, C. Please try to do this question. Clear? Take 1 or 2 minutes. Think about the question. After that, construct the Moore machine. Okay, see. Produce A as output if input end with 1 0. This is the initial state. 1 Q1 0. End with 1 0. It produce A. If input end with 1 1, it 1 1, it produce B as output. Otherwise C. Clear? Now make this as deterministic. 1 1 0, it produce A. Okay. 0. What is the transition on Q2? Please see what are the transition on Q2. 1 0 1 and 0 this one. Please check this is correct or not and make the transition table for this Why we make the transition table? Because when will we see conversion Moore to Mealy machine, transition table play the important role. See transition table for this. Input alphabet 0 and 1, output associated with the states Q0, Q1, Q2, this one is Q3. Output associated with the Q0 is C, Q1 is C, Q2 is A, and Q3 is B. Q0 on 0, Q0, Q0 on 1, Q1, Q1 on 0, Q2, Q1 on 1, Q3, Q2 on 0, Q0, on 1 Q1, Q3 on 0 Q2, Q3 on 1 Q3. This is the transition table. Clear? Next question. Construct a Murray machine that takes binary number as input, and produces residue modulo 3 as output. What do you mean by this? What do you mean by this? Residue modulo 3. When we divide the 3, a binary number, the remainders are output. It means input alphabet is 0 and 1 and output alphabet is 0, 1, 2. How many remainders are possible when we divide 3? Only 3. 0, 1, 2. Please try to do this. Do fast. Yes. Have you done this? See. There are 3 states are possible because 3 output alphabet. Q0 associated with 0. Q1 is associated with 1. Q2 is associated with 2. Suppose 0000 is the binary number. Convert into decimal. The decimal number is 0. When we divide 0 by 3, remainder is 0. If I see 1 on Q0, the decimal of 1 is 1. 1 divided by 3, remainder is 1. It goes to state Q1. After seeing 1, we reach on Q1. If I see 0 on Q1, then number is 10. The decimal number of this is 2. 2 divided by 3, remainder 2. It goes to Q2. After seeing 1, we see 1 on Q1. This is 3. 3 divided by 3, 0. After seeing 1 0, we reach Q2. If I see 0 on Q2, the number is 100. What is the decimal number? 4. 4 divided by 3, remainder 1. If I see 1 on Q2, this number is 5. 5 divided by 2. Sorry, 5 divided by 3, remainder is 2. This is the Moore machine for that. Please check. Clear? What is the transition table for this? 0, 1, output alphabet, state Q0, Q1, Q2. Output associated with Q1, 0, 1, 2. Q0, Q1, Q2, Q0, Q1, Q2. Please check this. Clear? See next question. Construct a Moore machine, that generate an output X for every occurrence of A in the input string otherwise it generate output Y consider input language is over the symbols of A's and B's. Do first. Do fast. What is the input alphabet? A comma B. What is the output alphabet? X and Y. Delta is X and Y. Sigma is A and B. Clear? Clear, my dear? Okay, see. When we read A on Q naught, it prints X. Otherwise print Y. See. Clear? What is the transition table for this? Output alphabet X, Y, Q naught, Q1. Q naught on A, Q1. Q naught on B, Q naught. Q1 on A, Q1. Q1 on B, Q naught. Clear? Next question. Construct a Murray machine, that generate an output X for every occurrence of AA in the input string, otherwise it generate output Y. Consider sigma equal to AB. Please try to do this. Yes, see. Q naught, read A, Q1, read A, it prints X, otherwise it prints Y. B, what about the B? B, A, B, A, no. This is not here. This one is here. B, B, A, this one. Please check this. Please check this. If I give the loop here, it prints ABA for X. That is not correct. Clear? Next, ones complement of a binary number. Construct a Moore machine for ones complement of a binary number. Construct a Moore machine for ones complement of a binary number. See, input alphabet is 0 1, output alphabet also 0 1. If I give the input 0 0 1, the output will be 1 1 0 1 1 0. Clear? Do fast. In binary complement, we assume machine reads a input from right to left. Please listen carefully. In complement questions, we assume that machine reads the input from right to left, not left to right, right to left. We assume that. See, Q0. It reads 1, print 0. It reads 0, print 1. When we read 0 on Q1, it prints 1. When we read 1 on Q1, it prints 0. See, this is the ones complement. Ones complement. The output for this is this one. Clear? If I add any number of zeros in MSB, there is no change. There is no change. Clear? No. Next. Construct a Moore machine. Construct a Moore machine for 2's complement of a binary number. Construct a Moore machine for 2's complement of a binary number. See how to find out the 2's complement. Suppose input is this 0 0 0 0 1 0 1 0. What is the 2's complement of this? Read the input string from right to left. MSB to LSB. Sorry, this is LSB and this is MSB. Write 0 as 0, first one as 1, after that complement the number 1, 0, 1, 1, 1. This is the 2's complement of this. Assume that machine reads the input from right to left. Please construct the machine. See. Please try to do this question. This is the input. Suppose this is input. Clear? Read any number of zeros from right hand side. The output is 0. When we see 1, leave it as 1. After that, complement the number. After that, complement the number. When I see 0, it becomes 1. When I see 1, it becomes 0. On Q2, when I see 0, it becomes 1. When I see 1, it is 0. See, this is the 2's complement. This is the 2's complement Moore machine. This is the 2's complement of Moore machine. Now, Moore machine is over. In next lecture, we will see Millet machine.